This is Sandeep Mandal from DES Engineering, and basically I am currently working on various CFD projects such as vortex shedding, gearbox sloshing effects, and many more. So I have decided to make one video on basic CFD simulation. In this video, you have to learn how we set up a fluid flow environment in Fluent setup, and I am also providing one basic file for space claim so that you can practice it at home. It is just like a tutorial. Thank you. Now we have to set up a simulation for fluid flow coupling. It is just like a coupling and a fluid flowing into it. I'm giving it as a curvy shape. Also, I'm sharing the model with my driver link on the description section. So let's begin with ANSYS Fluent. First, you have to open ANSYS module. So this is the ANSYS module, and we have to perform a CFD simulation. So I'm dragging fluid flow fluent. After dragging a fluent, you have to import a geometry into it. So I'm opening a space claim by double clicking on geometry section. So you'll see here in a below startup window, it is opening. So space claim is successfully opened up. Now you have to drag your geometry, so go to File Explorer, and here is my file, fluid flow coupling, and I'm dragging it directly. It's a SolidWorks part. So it will take some time for importing a geometry. Now the file is successfully imported in the space claim module, and you'll see it's just like a pipe. Coupling is there. We don't need this file. We have to extract a fluid flow volume from this conditions so that our fluid is flowing into that. So what we can do here, we have to do pre-processing settings. So if there is extra edges, we have to remove that. So this edge is extra, so we have to go for repair, and we have to remove extra edges. So it will automatically find this red color edge, so we have to remove that. Now we don't need these couplings, because we only required this mid portion for our simulation, so you can delete it. Now this is the geometry which I have to pre-process for our CFD simulation. So what we can do, we are extracting a volume, internal volume, and that will be our fluid flow region, and I'm giving it a name as inlet and outlet from this side and this side, and I'm providing a fluid as a water from this side, and the water is flowing from other side, but there is a contour section, there is a elbow type region, so that there is a change in pressure of water flowing into the pipe, and also the velocity, and we are getting a different mass flow rate at the outlet section, which I have provided at inlet. So I'm going to perform a steady state analysis in this condition. So let's begin with pre-processing setting for this model. Go for prepare, volume extract. From this volume extract, we are going to extract internal volume. So I'm going for the edge selection method, and select this edge, internal edge, and select this internal edge automatically. You don't have to press Ctrl key for that, and click on OK. So your fluid region is generated here. You'll see here. So this is the fluid region which I am looking for, and this is the only region from where the fluid is flowing from this direction and coming out from this direction. We have to suppress that body so that it won't affect in meshing module. After doing this, you have to save a model. So you can save as a desired location which you want. Here I am saving it here as a final design. panel. So I successfully saved my geometry here, and now close the space clean. So you see there is a question mark. There is a question mark here. It means that our geometry is not successfully imported yet. So I have to, the file I have previously saved, I have to import that. So right click on this geometry panel and import a geometry from browse. So you have to drag that final body. So you will see tick mark here. So after the successfully importing of geometry, we have to go for meshing section. In this meshing section, just double click it. It will start a meshing process. Now the meshing module is successfully opened up and our geometry has been uploaded successfully. Now I'm going for the meshing section, and here I'm selecting as 8 mm as my mesh and generate mesh. It takes some time to make a mesh. You can go for even finer mesh, but as per the showing tutorial showing purpose, I'm going for the 8 mm mesh. As the geometry is evenly distributed, so our mesh is hexahedral, cells are generated here. We can also go for tetrahedral mesh, but how to go for tetrahedral mesh? Just click on right click on mesh, insert method, and from method select this body, apply, generate a tetrahedrons. So now if you generate a mesh, that mesh should be a tetra elements of elements are generating on that. So here you will have that tetrahedral mesh. You can also go for even finer mesh. I'm just clicking it at 4 mm and updating it. So 4 mm of minimal element was generated in this meshing condition. Now it's time for named selection. So you have to define an inlet and outlet geometry condition. So this will be our inlet. Just click on this face and click N from your keyboard, and this selection name pop-ups. So type inlet and click on enter. Again do the same procedure, click on this surface, type N and set outlet. So inlet and outlet was defined properly. Okay, then our meshing module has meshing procedures or pre-processing condition for meshing is done perfectly. Now it's time for going for pre-processing in Fluent. Set up a fluid flow region and many more conditions are there. After closing meshing module, this bold sign is there. It means that geometry has not updated properly. So right click on this and update a geometry. Now after updating it, right click is there. Now go for setup. So Fluent is starting. So here is a pre-processed Fluent launcher has opened up. I am going for the double precision method. If your laptop having a more than 2 processors, you can go for parallel processing and just selecting number of processor from here. But for this analysis I am going for the serial analysis, serial purpose. So it seems that Fluent is successfully opened up and our graphical window geometry is fully uploaded. So here you will see blue color, it's indicating inlet region, and this red region is indicating outlet. So this is our fluid volume, you can see. So for Fluent setting we have to go for steady state analysis. So let me tell you what steady state analysis is. In steady state analysis we are looking for end-to-end result condition. We cannot iterate a result in between time steps because we are not specifying any type of time step here. So steady time will be steady and the flow will be iterative. The pressure based analysis is there, absolute velocity formulation will be absolute. Now we have to define a gravity for our fluid. So from here you can see that y direction. So I'm giving a gravitational acceleration in negative y direction. So put it minus 9.81. So after providing a gravitational acceleration in negative y direction, it's time for other condition to set up. Now just go for viscous model. We have to set up viscous model. Go to physics, model, viscous model. So so in the viscous model I am choosing K epsilon model. So what this means, K epsilon? So this model is used for wherever there is a turbulence in flow. So I am setting up a inlet as pressure inlet, and I'm giving it as 20 megapascal, so that the water will be flowing at 20 pascals at the inlet and extracting out from the outlet. So for the K epsilon model, we are going for realizable condition and scalable wall function. So these two conditions showing a accurate result, not that much accurate, but for considering steady state we have to choose this only. Click on OK. Now time for setting up of material. So create edit. Now the default material which Fluent has taken as air, so we have to go for Fluent database. So in the Fluent database you have to select water, so drag it this arrow and you will get water liquid at third last. So click here and you have to just copy and close. So you would see that air and water, both liquids are here. So we have to select only one. Go for air and delete it, but air is not deleting because it's a default material, so we have to set water as default. So close this, go to cell zone conditions, volume. After this, open up water liquid. We have to select a material type as water liquid as a default for this condition which we are going to perform, and click on OK. Now again go for material, and now if you select air and delete it, it was deleted automatically. Not automatically, we are deleting it. So now you have only water as a liquid in this condition. So click on close. Now it's time for setting up of boundary condition. So double click on boundary condition, select inlet. We have to give it as a pressure inlet. So pressure inlet. We also can provide different inlet velocity, but we are going for the pressure inlet. So gauge total pressure, I am giving it as 20 and OK. So and other conditions are remaining same because it is automatically detected by Fluent what to do with that condition. After boundary condition, I have set up a turbulence model. So there is one question: how would I know the fluid is flowing at it's turbulent, not laminar? So there is one thing you should know about this. Go to solution, initialize, standard initialization, and go to option. In this option, compute it from inlet. So the x, y and z velocities are automatically calculated, and turbulence, kinetic energy and other tools are. So with this value you can manually calculate whether our conditions are lying into turbulent region or laminar region. I have calculated it. It is lying into a turbulent region. That's why I have selected K epsilon model. You can also calculate this velocity manually by using Bernoulli's theorem or continuity equation. But if you don't know that concept, you can go it for software. Software is automatically applying that condition and giving you velocity and other regions. Now initialize the process. After initialization, initialize it. Now we have to define a condition, so definition condition. So this flux report is there, mass flow rate. We have to know what is the mass flow rate at outlet. So click on outlet, report a file, report a plot, print to console, and click on OK. So after initializing and setting up what we desired at end result, we have to go for graphics. We have to set up for solution condition what we want to see in our analysis. So go for result. We have to create a plane on which I want mass flow rate or velocity. So going for plane, I'm going for this point to normal. So you'll see my plane should be normal to z direction, and by x and y should will be 0. So ix should be 0, iy 0, and iz 1, so that our plane is created at mid of this portion. So create it. So you'll see plane 4 is here. Now define a contour. We have to go for new contour. I want to see velocity magnitude at plane 4. Okay, and banded condition contour lines. So save and display. Sorry, plane 4, save and display. So you'll see here, it is after initialization some velocities are calculated with minor regions at the ends. You'll observe that. Okay, after calculating we'll get a defined result. So now it's time for setting up of animation. So go to solution, create animation, solution animation. Now go for this contour, select use active, so that this orientation will be set as default for our animation. Click on OK. Now it's time for giving it a run calculation setting. So go for run calculation, and since I am using a steady state analysis, I only have to provide number of iterations. So I am giving it as 100 iteration. It will be sufficient for this analysis. Now hit calculate. So during calculation it will calculate residuals plot and our mass flow rates and other animation. So successfully all the residuals are calculated. We have set for 100 number of iteration, but it is calculating only for something 72 or 75, because if you go for console, the converging solution is at 72 only. So after that there is no point for, because the repetitions or the residuals are repeating continuously after 71, 69, 70, 71, 72. That's why it is stopped, because there is no reason to calculate same value again and again. So here is our mass flow rate graph. It is reducing continuously. So why there is a negative volume, negative mass flow rate? It is not negative, it means that the volume is contained at the outlet section. So because of this contour regions, the mass flow rate is reducing continuously at the outlet. You'll see. So at inlet, 20 megapascal pressure inlet is there. The fluid is flowing from this direction. When the fluid is flowing, the boundary regions having a minimal velocity, because there is a friction at the center portion. The velocity is very large. Because of this contouring region, there is a small decrement in dimension here. That's why. And you'll see all the velocity plots here, and we can also run an animation for that. results, from animations, solution animation playback, and if you hit play, the animation will be running, how the flow is going through. And from this region, the velocity is, there is an increment in velocity with the help of this region. So in this way the flow is taking place here. So close this. Actually we have to pause the animation first and then we have to close it. Now go for report definition, and here, and if you want your, this is the console section, if you want your mass flow rate at console window, you can hit calculate, and here it is, mass flow rate at outlet. This console window is completely working on Python programming. You'll see there are different iterative equation which has been calculated or solved here. We can also view these results in a different forms and different animation forms in a CFD post. So let's go for that. Close this Fluent. After closing it, we have to go for CFD post. So Fluent is successfully closed and solution is generated. We can see that right mark here, and go for result. Double click on result. It is starting CFD post. So this is the CFD post interface, and it is totally designed for better visualization of our results. So this is the wall, internal wall. This is the volumetric region from the fluid is flowing. So I'm just clicking it, rendering it with transparency of this, and I'm just going for constant variable. You can see the velocity. Let's see velocity, apply. So we can get up, we have to create plane, so for creating plane, it insert and location, plane, and create a plane. So we have to define a direction. So plane will be, let's see, yx, xy. So apply. So you'll see that here plane has been created. Now we can render a plane with different variables. Let's go for pressure. If you hit pressure, so you'll see the pressure region. So pressure is increasing at this section, and reducing at this section. So, and again if you go for velocity, so this is the velocity region. Velocity is low at this portion and it is high at this region, mid region. Let's again go for some vector contours. So just click on vectors, location at plane, okay, and apply. So you will see the vector plots, velocity vector plots. Again go for this now. So this is the vector plots you are getting here. If you go for streamlines, again you have to start from inlet and apply. So now hide it. So these are the streamlines for fluid flow. So you can increase the spacing. I'm increasing it as 100 and apply. It will take some time. So you'll see the fluid is flowing in this way. Okay. So that's all for now. This is how we set up a fluid flow simulation. So this is how we set up a simulation in ANSYS Fluent and visualize the different result in different domain. So thanks for watching this video, and also I hope you should practice this at home, those who are interested in CFD. Thank you.